Hello, everybody. I think that this should work. Let's see. Do I have a microphone? I think so. Yes. Good. All right. Oh, hi. It's nice to see you all again. This time it's not going to be on Instagram Live. It's just going to be on YouTube, which means the bandwidth should be a little bit better. And this time is going to be different in that I'm going to be streaming in space. I'm going to be using a piece of software behind me called Space Engine, and we're going to be able to look at the things we talk about, which is really exciting. But just like last time, if you have questions, you can put them in the chat, and I'll get to them. My name is Kevin. If you don't know who I am, if you're just randomly stumbling on this, I'm an astronomer at the University of Arizona. In my spare time, I like to talk to people about space, of which you can see some back here. You can see some aurora, and this is all fake aurora, but I really think it's very pretty the way that it's faked in Space Engine. Today, if there's not any questions, I thought that what I'd do is I'd talk a little bit about stars, maybe just give like a little lecture on some stars and some stuff you can see in the night sky, which might be fun. But if there are questions, you just put them in the chat, and I'll hopefully look down here and see them. Here, in fact, I can write, here's the chat. Here's the chat. Boom. And you can ask questions there. But otherwise, I'll just do rambling, which I'm very good at. So let's switch over to a smaller version of me so I'll get out of the way. Whoop, down here. So this is Space Engine here. Space Engine has a bunch of windows that are going to pop in and slide in. But Space Engine, the whole thing, and here, let's pause the simulation right now. Actually, we'll zoom out. Is that Space Engine allows me to fly around in the universe. I can fly through the aurora here. I can go a little bit lower, go into the atmosphere, and really fly down through here. Woof. So now we're below the atmosphere. Really just motoring. But let's get out into space because it's Space Engine. And here, I'll increase my speed a little bit. And now, there's the Earth, huh? Pretty nice. We're a little bit askew. That should be a little more familiar to people. So can you guys recognize America here? Hopefully you can see my mouse. You see Florida. And if we put it right now instead at pause it and put it at our current time and just press play, this is what it's like right now, where the East Coast, if you're watching from the East Coast, it's dark out, but the light from the sun's over here, real bright, is just barely crossing over into the Great Lakes region. Well, I guess it's a little past the Great Lakes region, and on into the Midwest, right? Pretty cool stuff. I'm over here. Apparently it's cloudy, according to this right now. I don't know if it's cloudy outside for real. I think it's pretty sunny right now. And over here you can see the aurora at night up over Europe, which is very pretty. So if you've never seen Space Engine before, it's really incredible. Here, watch this. Watch this. So if I just get right up like this, we can change the settings and like really make a very pretty exposure. We can drop it so you just get the sun coming up over. I like this because now you can see right through the atmosphere there with the aurora, just the bands flying over, which is pretty cool. So back over here, let's start looking out at the universe, okay? And so for people who are at night already over on the East Coast, we can land. Let's land right over here. Where are we going to land? Whoa, well, I guess right there. So now we're landing in the middle of the ocean. Can't see the sun. And you can see all these stars up here, right? And we can actually make it a little bit easier for us to see stars by like really bringing these in. So you can really see the stars in the Milky Way here. Most places, you don't get that great of opportunity. Whoops. The stars, there's not that many stars. It's more like this. But we, here in this amazing program, can really look at stuff like this, right? So if I pause it, boop, which you can also not do, and we look up, we see quite a few stars, right? Maybe 10,000 stars you can see in a good night. And there's some objects that are a little bit brighter. If we were to click on this, here I can bring up some stuff. You can see this is Venus right now, okay? The planet Venus. And in fact, let's drop the starlight a little bit just to make our lives a little bit easier. Venus is something you can see outside if you're in the northern hemisphere and it's clear right after the sun is set. The sun will set right over here to the right. In fact, if we fly up into space, you can see as we fly up into space, eventually the sun will rise over here. There it is. So there's the sun. So right where the sun has set, you look up just a little bit off of the horizon, you'll see Venus. It's the brightest thing you can see. And that's a pretty good guidepost, especially because right now, so let's center Venus here. And let's zoom in like we've got a telescope, which is the cool part about this. If we zoom in, if we can page up, we can zoom in. You can see Venus is next to something pretty awesome right here, which we'll talk about in a little bit. Right here, you guys can see this awesome group of stars, which is called the Pleiades. It'd be pretty hard to see the Pleiades because Venus is very bright, but with our technology here, with our program here, we can see the Pleiades. We'll talk about that in a little bit, right? The Pleiades is in the constellation of Taurus the Bull, and you can see next to the Pleiades and Venus, you can see the V right here, which is the face of Taurus the Bull. And Taurus's horns come up this way, right? Big horns. Big bull. And Taurus is right next to maybe the most obvious, easy to see constellation ever, which is right here, and this is Orion. So Orion's got a head here, 2 shoulders, her waist is right here, this is her sword, her legs come down here. You may be saying, wait, isn't Orion a boy? Orion's whatever you want. It's a constellation. And next to Orion is in the sky, Sirius. Sirius is an incredibly bright star. And also you can notice right here, a really cool globular cluster next to it, which we'll talk about in a second. But Sirius is also known as the dog star. And it actually consists of 2 stars. In fact, I think it's trying to simulate that here. I think if you click on this one right there, no, maybe not. Maybe it's still trying to simulate Sirius. But Sirius is a pair of stars. And it's part of Canis Major, which is the big dog. And you can turn on stuff in this program. You can turn on and look at the constellations, right? But it's not as exciting as just looking at them ourselves. Uh-oh. Someone is asking about stars getting really close and maybe too close and hitting each other. And so let's answer that question with Sirius, right? So let's actually go to Sirius right now. This was cool about this program. We can actually go there. So stars are very small compared to how far away they are, right? I mean, there's a lot of empty space. We're flying through space right now. We're a parsec away, 3 light years away from it, and getting faster and faster. But there's a lot of empty space between us and the nearest stars. A lot. So here they are. Boom. And the thing is that these 2 stars are really far apart, even though they are in a binary orbit. So these 2 stars are orbiting each other. In fact, we can turn on, I think, a little thing here. We can actually make their orbits appear. And so you can see that they're orbiting each other. And it's kind of weird. You might be saying they don't look like they're orbiting each other. What are these lines? What's going on? So let's increase our speed. So here. These 2 stars are orbiting each other. And if we put this and we track it, so let's track it. And then we actually click and make the stars go faster. So let's increase our time speed a lot. So now notice, these stars are orbiting each other, right? Watch as they go around. Whoop, and they're going back around. Isn't that neat? Now, we're going really far into the future right now. This whole thing, we're in 2060, 2070, 2073 right now. We're really whipping around. But you might say, well, do they crash into each other? Well, so let's go back to now. Well, let's look at how big these stars are. All right, so let's actually check this, and I'm going to change the HDR, and I'm going to lower my exposure quite a bit. Actually, let's lower my exposure quite a bit. We're going to zoom in and look and see when we can actually see this star. Whoop! Whoa, we got really too close to the star. So let's back out. So here's our star. This is Sirius A. We're really close to the surface right now. I crashed into it accidentally. And if we look at Sirius B from, in fact, let's turn off our ability to, let's pin this. And we turn and look at the other star. The other star, so if we, way over there, if we center that, Sirius B, and really zoom in, we're really zooming in quite a bit. We're zooming and zooming and zooming. And zooming and zooming and zooming. And it's really hard for us to actually see this object. It's incredibly far away for how close these 2 stars are. These 2 stars are orbiting each other. They're right next door. But they're so tiny compared with each other. They're really big, but they're just incredibly far away. And so it'd be kind of like if we were in our solar system and you took the sun and you shrunk it down to the size of a grapefruit you were holding in your hand, the nearest star would still be in Peru, really far away. And what that means is that stars never, hardly ever crash into each other. Maybe when they're dead, long time in the future, they might, over a long period of time, spiral in on each other. But generally, stars don't crash into each other ever. And so even these 2 stars, which are currently in orbit around each other, are still so far away from each other compared to how small they are that they're just never going to crash into each other until way far in the future. Pretty incredible. So let's go home. Back to Earth. we got to travel here. I'm going to turn back my HDR and put it on here. So we're going there. Again, look at how much empty space. Star Trek makes you think that stars are flying by, but we're really motoring to the nearest star, which is a couple parsecs. You know, we're motoring to the sun, and it's still, you know, whew. All right. So I'm going to turn the orbits off because that's a little distracting at the moment. And so all these stars are incredibly far away for how small they are, which is, you know, a bummer if you want to go there, right? Like the nearest star, Alpha Centauri, is still quite a ways away, right? And in that period of time, we're not, you know, it's not likely that we're going to ever, oh, whoops, I don't want to be there. We're in a human lifetime, we'll make it to the nearest star. All right, so where were we? We were looking at, oops, I think we have to rotate our way around like this. Here we go. This makes more sense from the Northern Hemisphere point of view. So, what I want to do is I want to talk about stars right now. And I want to talk about stars by talking about our star, the sun, first. So let's go to our star. Let's center on the sun. And you're not supposed to look at the sun, but we're going to go to the sun right now. The sun is located 1 astronomical unit away. And it is pretty big. You can see up here the diameter in miles, which is 864,573 miles across. Here it is. Whoops. And if I zoom around, you can see right now we've got it where the sun is essentially like allowing us to see what the surface looks like. If we were to turn off this HDR and just like, you know, it'd be, that's automatic. I'm changing it. But like if we ramp it up, you'd see what the sun generally looks like. But we can make it so that we put some nice filter on and we can really see it right now. So I'm going to show you what it looks like, what the Earth looks like from the surface of the sun. Are you ready? So if we zoom around, so let's actually land on the surface of the sun. Not a good place to be, but whoop. All right, and so now I'm going to center on the Earth. This is what the Earth looks like from the surface of the sun. Right? Now we're currently gimbal locked, which is why it's doing that. But if we were to zoom in, look at how long it takes for us to use a telescope. There you can see the moon now. Now we're finally seeing the Earth through the telescope zooming in, right? So it's not like when you're on the moon and you see the Earth, you know. The sun on its surface is thousands of degrees. Thousands of degrees. All right? You can see over here that the temperature right now is, it says only 56, I don't know why it's saying 56 Fahrenheit. Oh, that's because it's the Earth. But you can see here, like, the sun's surface is really big. If you were to zoom out of the sun and look at it from far away, to give you a sense of the scale of the Earth compared with the sun, 100 Earths could fit across here. 1 million Earths could fit inside of the sun. 1 million Earths fit inside of here. It's really big, right? These spots on the surface are called sunspots, and generally, you know, a couple Earths could fit across them. Whoop. I keep crashing into the Earth because it's hard to. We're in a sunspot right now, and even inside of these sunspots, it's still thousands of degrees. It's still very, very, very hot. These sunspots are spots where it's slightly cooler because of the magnetic field of the sun. So the sun is a giant ball of hydrogen gas. Hydrogen gas is all over the universe. In fact, most of the universe is made of hydrogen. There's a little bit of helium in the sun as well. And what the sun does, just on a day-to-day basis, is the sun inside its very core, where it's millions of degrees, it takes that hydrogen gas and pushes it together to make helium gas. And then eventually it'll take that helium gas and push it together to make carbon gas. And the thing is that the sun, in its core, it's like the bottom part of a boiling pot of water. The boiling part of the bottom right now has the heat element, and it heats up. And the water, when it gets warm, it moves up to the top and cools down and goes back down and bubbles. It's rolling boil. And the sun is doing that with gas. Where in the very center, it's very, very hot. That hot gas is rising. It will eventually cool down and then fall back down. And you're seeing that, which is why the surface looks the way that it does. So if I slow down, you can see that the surface has all these like weird little marks on it. These are called granules. And these granules across the surface are essentially parts where it's boiling. I wonder, I don't think it's going to be the case, but I think if I start doing this No, it's not going to do it. It's not going to simulate the granules. But the granules over time will change because these are pockets of hot gas that are rising up to the surface and then falling down. And inside of the core of the sun, there's a magnetic field generated, just like in the core of our planet Earth. And when the magnetic field comes out of the surface of the sun, it interrupts that process of heat transfer and makes cooler areas. So this is an area where the hot heat from the very center of the sun can't easily get out because of the magnetic field lines. And you can kind of barely see they've simulated little curves as they go away from these. But that's what makes sunspots. Sunspots are just made by the magnetic field of the sun interrupting heat transfer from the very center of the sun. Our sun is a fairly standard sun. There's many, many suns like it. It is what's called a G-type star. So it's up here, spectrum G2V. And there are many types of stars, O, B, A, F, G, K, and M type stars, and then some other T's and all sorts of other stuff. But generally, this is the spectral sequence of stars. O stars are blue and very, very hot. M stars are very, very cool and red, and I'll show you guys examples of those in a bit, right? So it's a pretty standard star. It's in a part of its life where it's just taking hydrogen, turning into helium on what we call the main sequence of stars. It's just what stars do. Around the edge of the star, it gets incredibly hot again, but the gas is very, very tenuous. There's not very dense gas, and that's this corona here that you can see on the very edges of the star. In fact, if we were to go to the Earth, let's get there really quick. Whoop. Let's turn around and then find the moon. Let's see if I can find the moon really quickly. Moon, center the moon. Let's zoom in on them. Let's fly to the moon really quickly. Whoop, whoop, whoa, center that moon. Whoa, gosh, I'm going too fast. All right, so let's center the moon again. And let's, nope, center the moon. All right, here we go. Oh. Whoa, gosh, I am not able to center very well. But if we fly over here and then move up, this is tough challenge. There we go. Now let's zoom away. There we go. And simulate an eclipse. Whoop, 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 whoop. You can see as we, so I want to center this. Don't know why it's not allowing me to zoom in, but if we, and then really, oh man, we're seeing a lot of stuff. We got to get right. So we just keep flying back, keep flying back. You can see right there. Here, let's zoom in. You guys see this? We're simulating an eclipse right now. You can see the corona of the sun. These are parts where the magnetic field of the sun is pulling charged particles up into space. These plumes, these prominences, solar flares, and the sun's very active. So sometimes it burps a lot of gas along those magnetic field lines off into space. Pretty cool. So let's go back to the Earth. I'm going to keep going back. Let's go back to the Earth. That was why I was not actually focused on the Earth, so we can go there twice. And from the Earth, again, so again, right now we're looking at East Coast one more time. You know, you can see South America right down. But if we just go and fly down to the, let's land on this right at, you know, in the middle of the Appalachians, and we look up again. I want, set the reset the exposure compensation. I think we're in a pretty bright area, so let's go to a darker area. Like here, space. I want to look at some stars here, and so let's start by talking about, like, we're going to talk about where do stars come from? So stars come from gas. They're made of gas, hydrogen gas, helium gas. If you get enough gas together, that gas eventually collapses to make stars. And so what we need is maybe to find out, well, all right, can we see gas clouds? Is there a way we see a gas cloud in space so we can actually see whether or not there are stars? So let's look at a gas cloud. So again, we're looking at the same area. You see Venus here. You see the Pleiades cluster, Taurus. If I turn on the constellations one more time, you can see Orion and Taurus next to each other. If we look at Orion here, we look at Orion's belt. So let's look over here and look at Orion's belt. I'm going to zoom in right now at Orion's belt. So here's Orion's belt right there. And below it is Orion's sword. And so if you look at her sword from far away, you can see that there's it looks like 3 stars in the sword. But actually, the center one, if we were to center that, and then really zoom in on it, is not a star at all. It's actually, just what I was saying, a giant gas cloud. It's the brightest part of a giant gas cloud because there's a bunch of stars in the very center of this gas cloud that are lighting it up. So if I change my exposure compensation, you can really see this gas cloud pop out. Pretty cool, right? This gas cloud is the Orion Nebula. It's named after Orion, the constellation it's in, and this is the brightest part of the Orion Nebula. And you know what? Let's go to the Orion Nebula. So I'm going to turn on my thing here. We're going to actually go to the Orion Nebula. So it takes a while because we're 400 parsecs away. Parsecs about 3.2 light years. So we're 1,200 light years away. So really, and you can see that some stars on the edges over here are actually kind of moving towards us because there are quite a few stars between us and the Orion Nebula. But that gives you an idea. If it's something you can see with your eye, it's actually incredibly, incredibly big. You can see the diameter up here of the Orion Nebula is 13.39 parsecs. That's 14 parsecs, 14 times 3, so 30, like 40 something light years across. Just this one thing. We're really, getting there. So now if we center it, we can really zoom in. Whoa! So let's slow down and let's look around it. Whoops. So I'm going to change the exposure compensation again because I want to show you that there are some stars in the very center here. So if I zoom in and we get really close, these stars here are the bright stars that are in the very center of the cluster that are causing a lot of the light that you're seeing here. And what's going on in this is these stars are actually lighting up and exciting the gas like a neon light around this. This big patch here is not lit up. It's just a bunch of dust in it. And that dust is actually also coming along with the gas, and it's blocking the light that we can see, right? You can see these bright stars here are fairly blue, which is pretty incredible. So if we center on this one here, which is called Theta 1 Orionis D, it's a blue main sequence star. It's a B-type star. And if we go there, get really close, it's very different than the sun. It's much, much, much brighter. And so right now, we're about an AU, we're the same distance that the Earth is from the sun, except this one is an incredibly bright blue star. So very different than our sun. It is blue and much, much, much hotter, right? It's actually 300 times the brightness of our own sun, right? I have to change the exposure compensation on here so you can see. But very similar to what our sun is doing, it's taking hydrogen and turning into helium in its core. And you can still see, similar to our sun, it has granules on the surface. It's just a huge amount bigger, right? So its temperature is 25,000 Kelvin, where ours is about 5,000 Kelvin. So way, 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 way hotter. And it is so hot, which means it's going to live a very short life. But right now, if we go back... So by the way, here's what, if we center the sun, this is what the sun looks like from the Orion Nebula, i.e. you can't really see it very well. We're trying to zoom in and see if you can see it. There it is. There's the sun. That's what the sun looks like once you zoom in through a telescope. Without it, it's too faint to even see. It's barely there. You can just barely see it. The universe is full of stars, and our sun is not a particularly bright, exciting star. It's So here we go. Orion Nebula. We're inside of the Orion Nebula because we're right outside, right next to the star. But you can see that living inside of a nebula is like, living inside of a bunch of gas. And the gas is excited and lit up, which is why it's producing all these colors. The destined nebulae are actually not as dense as you'd think. It's probably maybe what? I think, what is the IGN? What is nebula density? I've got to look this up because I don't want to get this wrong. But it's, it's measured in like numbers of particles per box meter. So let's look it up. 10,000 molecules per cubic centimeter. So, 10,000 molecules in every cubic centimeter, right? So that's like not a lot of molecules per cubic centimeter, right? Like your dust is composed of millions and a huge amount. Like, so you think a nebula is like incredibly dense, but it's actually very, very what we call tenuous. So let's go back to the Earth really quickly. I love these parts. You can see the Milky Way stretching across here. We'll get there in a second. And so once stars are born, Orion Nebula is a nebula that's currently creating stars, but there's quite a few different nebulae. And those nebulae, they come from gas that's from other stars. We'll talk about nebulae and stars, and we'll talk about that in just a second. But once that finishes, So now if we go and we turn around and then rotate again, once that process finishes, you've got a bunch of stars in a gas cloud. And so let's look at a gas cloud with stars in it right here. So if I go here to the Pleiades, which I talked about earlier, the Pleiades is a group of stars that used to be in a bigger gas cloud. That gas cloud collapsed and formed what we now call an open cluster of stars. Kent asks if the color of the nebula tells us about the composition. And for some, in the case of what we just saw, yes. In this case, it's different. It's slightly different. But in the case of the Orion Nebula, so if we look at the Orion Nebula from here, and this is going to be kind of fun. Orion Nebula. We center it. And we zoom in. Notice it's not in Orion right now because we're far enough away that all those stars that look like Orion from us don't look like Orion from this angle. So if we zoom in, I should always just click page up. You can see that there's pinks and some blues. That pink and red, so this image right here is taken generally from Hubble data that they put into this program. Or like simulated. But essentially, with Hubble, you can take a narrow filter and just only look at light of very specific wavelengths, like in this red. And what you're looking for is the fact that this gas cloud is a lot of hydrogen. Just like I said, hydrogen goes into making new stars. That hydrogen can get excited at a very specific wavelength because of, just like how neon light or other, like other gases can get excited by light from those stars. That light can hit that gas, get the gas excited. The gas then releases the electron falls down and releases light at a very specific wavelength. And in this case, the wavelength of hydrogen is 65, 63 angstroms, which is exactly our 656 nanometers, which is exactly the wavelength in the reddish. And so this tells us about hydrogen. So this is a fingerprint of the chemicals that are in the gas cloud. Exactly what you said, Kent. If we look back at the Pleiades, so if we zoom back out to the Pleiades, and then turn around to where these stars are, if we can find it again. We should be right next to it. Let's find it one more time. I don't know where it went. Pleiades. Pleiades. Okay. Pleiades. Oh man, I have bad spelling right now. Go to. There we are. At the Pleiades, it's slightly different. You're not seeing gas being excited in this. This is what's called a reflection nebula. So you're actually seeing light reflecting off of this gas. But it allows us to see the gas that's still in this cluster of stars. So this is a cluster of stars years after many of them have been born. That gas has been pushed away by the starlight, leaving a little bit of the remnant gas. And mostly here, you're just seeing kind of some of the last little bits of gas in this cluster of stars. So the Pleiades, let's see if I can get the correct age of this, is only 100 million years old. So this is relatively young in star time. If you're thinking, oh man, I'm 40, I'm 50, I'm 60, I'm pretty old. In star time, oh, you're a baby. Because this is 100 million years old. And this is essentially like elementary school right now. All these stars in the Pleiades, and we generally from the Earth can only see 6 or 7 of them. But there's, as you can see, a couple hundred in here. The really bright ones that you can see right now that are simulated, maybe there's 40 or 50. But the Pleiades is not a very dense cluster. We call it an open cluster. And gravitationally, it's not held together very strongly. And so as a result, if something were to come along gravitationally, it could pull those stars apart. Our sun was in a cluster just like this, 4 billion years ago, 5 billion years ago, and something came along and threw those stars apart. And so now you can go and find other stars and trace them backwards and say, we're probably part of the same moving group. We're maybe part of the same cluster at some point. All of these stars in this open cluster are the same age because they were born from the same gas cloud around the same time. And because they're born in the same gas cloud, they're all the same what we call metallicity. They're made of the same stuff, the same composition, as Kent was just saying about gas. The gas that's in the gas cloud is the same composition generally as the gas that's in the stars because they're made of the same stuff. And that allows us to do some really cool stuff. And I did this in college with a cluster. You can figure out how far away this cluster is and how old it is based on looking at the population of stars. Because while these stars look like they're all generally the same, if you click on individual ones, you'll see that some of them are A-type stars, some of them are B-type stars, some of them are and so this is an M-type star. I guess it's an M-type star that's much, much far away. But like you can click on these stars and see that they're the different F-type stars, and these types of stars mean like that some of them are hotter or cooler, and hotter stars go through their life cycle faster. So if you looked at the hot stars in this cluster, those cluster stars will have advanced farther in their life cycle than the cooler stars. But when their stars are born early on in their cooling cycle, they eventually become stars and then take the hydrogen and turn it into helium in their core. And most stars in our solar system, or sorry, in our galaxy, are stars that are doing just that. They're turning hydrogen into helium in the core. And so if we were to like fly through the galaxy at a really rapid speed, so if we fly right now, we can start seeing all these dots are stars. And if we just stop and like look at one, like this little one right here, we can click on it. This is a red dwarf, and this star is most likely, whoops, let's actually just go there. Most likely just sitting here fusing hydrogen into helium in its core, just like our sun. But it's an M-type star, so it's actually very much cooler. It tells us actually here, so this star, in Space Engine, they simulate some stars, and you can see here that it has one planet with life. Let's go look at that, actually. That's kind of fun. Here's the solar system on this red dwarf star. You can see this red dwarf, they simulated that it has one planet here, a hot Jupiter, so it's a planet that's really close to its sun and very hot. This is a warm super Jupiter. Here's cool arid Aquaria, cool super Jupiter, cold arid Aquaria, cold Jupiter, frigid arid Aquaria. I'm trying to find where the planet with life is. So if we zoom in, is it this one? Does this have life? Someone just banged next door. I'm trying to find where the life is on this one. Is it this one? Cold arid Aquaria? It must be on a moon of one of these things. Because some of these are way too far away. If we look for the Earth, hot arid Terra, it must be this guy. It must be that this is a hot desert planet that might be like the Earth. Anyway, this is a simulated star. You can see some of these stars are simulated to be very much like Jupiter with, spots as well. Pretty neat. So, if we go away from that, back to this, we can see, as I was saying, by a little planet, or a little star, that we have quite a few stars. And all of these stars, 100 billion of them, almost all of them, the vast majority, are taking hydrogen and turning into helium in their core. So if we go back to the sun, we could talk about what happens at the end of the sun's life. So the sun is going to live for another 5 billion years. Later on in its life, it's going to start taking hydrogen, taking the helium that's left over from making hydrogen into helium and turning that helium into carbon. But at a certain point, it will have a core that's composed almost entirely of helium with a layer of hydrogen around it, and it'll get very, very hot, and won't be able to, a core that's composed of carbon with a layer of helium around it. It'll get very, very hot, but not hot enough to take that carbon and fuse it and turn it into a heavier element. And at that point, the star will expand outward and form what's called a planetary nebula. And so the end of the life cycle of a star, like our sun, is not an explosion. It's just the outer layers puffing outward as it gets larger. And you can see other stars that puff outward if we go back and look at, say, this star right here, which is called Betelgeuse. So if we center that star and look at it and go there, Betelgeuse is 130 parsecs away, so really far away. Its temperature is 3,000 Kelvin, meaning it's actually cooler. It's less hot than the sun by a couple thousand degrees. But it's about 9,000 times as bright as the sun. Very bright, but but not as hot. And also, look at this. It's weirdly misshapen. It's got weird spots on it. What's going on? Well, this star is getting near the end of its life, and it has expanded outward, and it is incredibly huge. If you sat this star in our solar system, here, let's show you exactly how big it would be. All right, so let's go back to the sun really quickly, and let's zoom out, and turn on the orbits again. Boop. And we'll turn like this. So, here's the sun. This is Mercury's orbit, Venus's orbit, Earth's orbit, Mars's orbit, right? If you put Betelgeuse in our solar system, it would be this big. It would go all the way out to Mars, right? The sun is right here. It's not particularly big. Like if you zoom in, you gotta, it's right there where we can finally see it. Betelgeuse is so enormous because it's puffed out near the end of its life. And because it's so old, it's getting to near the end of its life, it has a bunch of really interesting surface properties where it's getting darker and brighter and it's belching out gas and dust into space for future generations of stars, which is pretty incredible. So if we go back to that star, let's see if I can find it really quickly. I think it's right here. I'm getting really good at finding it. Click on it right there. We go there really quickly. They've simulated it here as having, this little planet down here, which they've, Betelgeuse 1, a torrid arid Terra. Let's actually go to that planet. This will be fun. Let's see what it looks like to be on that planet. So, if we go and land on that planet right now. Here's life on the surface of the planet. Do you see this right now? What looks like the sun, the sky, and is actually an entire, here, I'll turn off the orbits, is actually the surface of the star. The temperature right now on the surface of this planet is 4,000 degrees Fahrenheit. It's incredibly, incredibly, incredibly hot because it's so close to the surface of this star, right? If there was life on this planet at one point before the star ballooned out, it's not life there anymore, unless it's very good at surviving incredibly hot. Let's get up here. I think this is a pretty cool view of what the surface, what it would look like to live so close. Pretty amazing. So Master Tatsu asks, could it be dead already? So we think that the star is going to die at some point in the next, 1,000 to maybe a couple thousand to maybe 100,000 years. What's this? What's this here? Looks like another object, maybe a rock that's been captured. Yeah, it's another little rock where it's probably even worse to live on the surface, no atmosphere, and you're just constantly with the star. So the thing is, oh, that's a nice heart. Happy romance there. So the thing is that it might die in the next 1,000 years. It might die in a year. It might die in 100,000 years. At some point in the order of thousands to hundreds of thousands of years, it might die. And the thing is that the planet, or the star, is not far enough away. It's not 100,000 light years away. So it's actually fairly close in terms of, like if we go back home and then look for the star again. I said I was getting really good, and then yes. So look at how far away it is. So if we click on it, it's 131 parsecs away. So multiply that by 300 light years away, right? So if it has exploded in the last 300 years, then yes, we wouldn't know about it yet. But more likely, it hasn't exploded yet because it's not going to be for another 1,000 years or 100,000 years. So probably not. This is why when people talk about, oh, maybe these stars are all dead, we don't know about it. Well, most likely not. The stars we see in our neighborhood are actually stars that are in, like if we zoom out to our galaxy, here's the Milky Way. Let's change our exposure again. Here's our galaxy. And let's just give you an idea of what we were looking at. So if I actually increase this, let's make it a little easier to see. All right, so this is where the sun is. So I'm focusing on the sun. So I'm going to zoom in. Our sun's over here, right? Now I'm going to look for Betelgeuse, and we're going to see how far away is Betelgeuse. I'm going to center on Betelgeuse. You ready? All right, I centered on Betelgeuse. So hardly any difference, right? If we zoom in, you can see there's Betelgeuse. And so now and Betelgeuse is one of the farther stars we can see, If I look back at sun and we center, zoop, that's it. Right there between the sun, which you can't even see in this, and Betelgeuse, that's the size right there. So it's not particularly, if we zoom out from here, you can see what we were just looking at. Like if I, I'm pointing on my screen, that's not going to help anybody. Remember, this is Betelgeuse over here. Look at how far apart, it's the size of my cursor. That's the region of space we can see. That's our neighborhood. That's the stars we can see. And so the thing is that most stars in that neighborhood aren't far enough away to have died appreciably. Now, some stars do die, but they generally die in other galaxies where they're far enough away and they become very bright. Betelgeuse, when it dies, will explode so bright, it'll be about as bright as the half full moon in the sky. You'll have a shadow from Betelgeuse at night, which is pretty incredible. But I don't know if I'll be around at that point to see that because that's quite a ways away. All right. I think I passed our sun. So if we go back to there it is again. So let's zoom out from it. When it dies, it will explode because what happens is, unlike our sun, actually, before I get into what happens to Betelgeuse when it dies, let's talk about what happens to the sun when it dies. So let's look at the Ring Nebula. So when our sun dies, its outer layers will puff out like Betelgeuse does, but the core won't be strong enough gravitationally to hold it there. And so the outer layers will puff out, leaving the naked core in the very center, and that naked core will heat up and excite that gas around it. And so the gas around that naked core will be heated up, and you'll see something like this. So this is one of the more famous things in astronomy. This is the Ring Nebula. And this is a planetary nebula. You can see it says type planetary nebula, where at the very center of the Ring Nebula, if we can find it, I wonder if we can find it. Yes, you can see it right there. Whoop, there it is. Bink. Whoa, no, 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 stop, stop. It's hard to click on this, so let's zoom back in. In the very center, and you can see it just barely right here. So if I slow down, I can catch it. Dink. In the center is the naked core of the former star that made the Ring Nebula. And if we zoom in, you can see it's actually got another object here. But this right here is what we call a white dwarf. And a white dwarf is a type of star that is composed of the core, all carbon in a crystal structure. And this carbon forms, is incredibly hot, but very small, maybe the size of the Earth. So this star here, this white dwarf star, is the size of the Earth. It's the leftover core of the star, and that core is glowing very bright. You can see the temperature is 5,000 Kelvin, almost as hot as the sun right now. But its apparent size is, much, 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 much smaller. 12,000 miles across, right? So if we change our, you can zoom in. Oof, it's very, 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 very bright. There we go. And it looks different. Doesn't have the granules. Oops, I've landed on the surface. It doesn't have the granules. Because it's not fusing. It's just cooling down. It's just a big hot crystal of carbon. Not a diamond, but a similar crystal structure that's just cooling down over a long period of time. Sometimes other stars, like you saw that there was another star that was around this, that was in orbit around this, and we can look at that one. So let's fly away from this again. If we go and turn on the orbits, we can see that there's another star. Maybe not. Maybe it's just on an orbit around itself. Oh no, yeah, here it is. This other star. And this other star is a red dwarf, so it's a smaller red star. It's still fusing. It's hard to see because I've turned my exposure so differently. It's a red dwarf. It's still fusing. But over time, if it were larger, it might start getting bigger and puffing out and giving its gas to the white dwarf star. And maybe that white dwarf star would reignite with some on the surface and you get a supernova. But for right now, what all that's happening in this, and so let's really zoom out, turn off our orbits line. What's happening right now in the very center of this is that naked core is lighting up with its heat all of the gas left over from the star's outer layers in this Ring Nebula. And so that's what all these colors are. And it's very similar to what Kent Clark asked. You can figure out what this gas is made out of. A lot of hydrogen, some oxygen, some heavier elements, some carbon, just by looking at the color of this. And so you can see that it's actually lit up other layers as well around it. And that's what's going on. We call them planetary nebulae because when we first looked at them, they looked like they were planets because they had different colors than regular stars, which is pretty cool. So that's the end result of our solar system. Is at some point it will become a planetary nebula. Our star will die. It'll slough off its outer layers into space and leave just this beautiful planetary nebula. And there's lots of planetary nebula. If you look up the Helix Nebula here, let's look at another one. We're going to go there. It's going to be a little bit of time. But planetary nebula are really good for your desktop backgrounds on your computer. If you just Google planetary nebula, you'll find some of the prettier astronomy images. Hubble really liked to look at a planetary nebula quite a bit. So here we go. We're zooming in. Look, another planetary nebula, right? Very different because the light is hitting a bunch of gas that's been sloughed off from the star. And it's a different geometry of gas, right? So if I zoom around here, you can see that it's a different geometry of gas. And if we were to go looking in the very center, we could probably also find the white dwarf here. It's a little tough because white dwarfs are small, but there it is, right there. Ding, 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 ding. Hello. Let's slow down. Thank you for dealing with the fact that sometimes I'm a bad driver. There it is. There's the little white dwarf. Right in the center, right? There. Whoops. I want to click on it and actually get it. Maybe it doesn't want to let me do it. All right, well, maybe it hasn't simulated the white dwarf. It's just simulated it here, which is pretty cool. So that's the end result of our sun. What's the end result of a bigger star like Betelgeuse? Well, Betelgeuse won't have the same problem, where as the outer layers puff out, the inner core isn't gravitationally strong enough to hold on to them and it just keeps puffing out. Instead, the core has held Betelgeuse, and so the core has held all those outer layers on, so it's puffed out, so it's so big, but the core is hot enough that it's been able to take that carbon and fuse it into heavier and heavier elements until it hits iron. And when the core becomes iron, at that point, the core cannot fuse iron into more energy and to make light. And so at that point, the power source in the center of the star will finish, and the star will start to collapse in on itself. The outer layers will collapse in on itself, and it will collapse down and explode in what we call a supernova. And so we should look up a supernova remnant. I wonder if I can see supernova remnant on here. There's Tycho supernova is a really good one. Is it called Tycho supernova right here? Yeah. So Tycho Brahe, although this is slightly different. This is a type 1 supernova. Let's look at the crab one. That's what we want to do. So we're going to go to another one. This is actually a supernova remnant. This is the remnant of a star that blew up thousands of years ago. The star blew up, and what you're actually seeing is the light percolating out still through all of the layers of gas around it after this explosion. This is the Crab Nebula. And in the very center is not a white dwarf. It's not the leftover core. It is the leftover core of the star, but it's a different type of leftover core. It's actually a neutron star. And a neutron star is what happens when the star collapses. It compresses down all of those neutrons, all that core, so that the core becomes entirely nuclei neutrons, incredibly dense. And it becomes a thing the size of Chicago. And if we go there, this is an object the size of a major metropolitan city, but it is essentially the mass of the sun or of the earth, like incredibly massive, compressed down, so it's incredibly gravitationally powerful. And it's got such gravity and magnetic fields are so strong that it rips particles. Woo! It's really bright. Neutron stars. So let's zoom away. We'll lower our brightness settings here. So it's in the very center here, this neutron star. And so if I zoom around it here, you can see that what actually is going on here is that it's in the very center is this star. It's taking particles that are falling onto it from this disk that's formed around it and sending them off into space in two directions. And so you see this jet right here on both sides. And here's something cool. It's spinning really fast. How fast? It's spinning about 1,000 times a second. So this is real time. An object the size of Chicago spinning hundreds or thousands of times every second. And so it creates this jet. And so if we put the jet towards our face, you can see that the jet pulses. Flick, flick, flicker, 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 flicker. And that pulsing, when seen from the Earth, makes it, we call it a pulsar. And so this is the Crab pulsar. It's the dead remnant of the star that blew up 1,000 years ago. As that core collapsed, it started spinning really fast. And it, created this incredible pulsar, this energy source, this light source. Pretty incredible. And this rate is so consistent, it slows down over time, that we can actually use pulsars as a map. There's been maps that we sent out to aliens being like, if you find us, here's how to find Earth. By looking for pulsars and how fast they're rotating, you can triangulate back to figure out where Earth is. If Betelgeuse were large enough, and I think it might be, if stars are big enough, then the core will collapse even farther from a neutron star and actually do something else. It doesn't just become a neutron star, it actually becomes a black hole. So now, let's see if I can find a black hole. So I'm going to pause this right now. And we're going to zoom out. I don't think we can see anything because I've really ramped up, but there's our So let's look for a black hole right now. This is a kind of fun thing. So if I do this, and we're going to look for star browser, and I want to do filter settings, and I want to do main star is a black hole, and I want to do OK, and I want to do search 100 parsecs. Nope, 100 parsecs. So let's find a black hole within 100 parsecs. There's one. Let's go there. So if it's large enough, it'll form a black hole. And so this right here is a black hole, the core of a star that's collapsed so far down that not even light can escape from the black hole. And you're saying, I can't really see it. What's going on? Well, it's black. It's a black hole. As we get closer, notice what it does. Weird, right? Light is actually warped around this black hole. I'm rotating it around. If I zoom out, whoop, you can see that I'm rotating around. I'm actually flying around it. But from our perspective, gravity is actually warping it, warped around it, and you're seeing the light going around the black hole. Because light, when it falls into the black hole, will never escape. But light, as it skims near the black hole, will get bent as it goes around. And so you can see as I rotate around that like a star, like this star here, watch as it should be going behind the black hole, but instead you can see that it's smeared out to make these rings of light, these arcs. And these arcs of light, these gravitational arcs of light, you know, you can actually see the same star in two different ways. This star right here is the same star as the one you see over on the other side. You're seeing it warp entirely around the backside of this black hole. This is me attempting to look at the universe now from the surface of a black hole. You can see how it gets really weird and warped here. Whoa. This is the arc of the Milky Way from very near the surface of a black hole, right? So this is just one of maybe a billion black holes that are in our galaxy, remnants of stars. And if enough of them, you can see here compared to the Crab Pulsar right over there. There's Crab Pulsar, right? Crab Nebula. You can see it just happens to be floating through space right here, right? Pretty cool as it floats. If we lower our, you know, you can see as it floats, it'll actually. So see how I did that right there? That's a cool thing. This is a really neat aspect. People wanted to study. If you wanted to study free-floating black holes, you couldn't look for them, right? It'd be hard to look for them. However, let's look at this star right here. This is exciting. I think this is a neat teachable moment. Let's look at this star right here. Let's center on this star. And we'll zoom in. So this is a star right here. It's a yellow dwarf star. And the black hole, as we do this, as we move, is going to be moving towards the star. And watch. Watch the star is going to get really bright right here. Look at how bright that is. Because the star is now right behind the black hole. It's right behind the black hole. And then we move back, and now you can't see it. And now you can see it again. But right as we go past it, it gets really bright. And we can measure this. We can look at stars over time and see ones that peak. Now, if we zoom way far back away to our original, look at that incredible arc right now. So let's zoom out. And we get it right there, right? This is a moment where the star is actually making a perfect ring because we're in an exact, like right on the other side of this black hole. And so the black hole is actually magnifying and making this look brighter. And from the Earth, we wouldn't see this ring. It's too far away for us. We wouldn't, like generally, but like if you're really, really, really far away, it's hard because, you know, like the thing is like exact. But eventually it'll look like the star that we can see is fairly dim suddenly comes bright and then dims down. And we've seen this. We've seen free-floating objects in space that have magnified the light in this exact way. And they've told us about the numbers of these types of objects in the universe. So that's it for generally the end of this. I want to, if there's any more questions, I got some good questions here. But if you have questions, please let me know. But like that's the life cycle of a star. From a gas cloud all the way to baby stars, like you saw in, you know, if we go to some more baby stars here, if we look at, say, the pillars of creation. So this is a thing that Hubble looked at in the Eagle Nebula, another nebula of young stars. If we go there a little faster, You can see the pillars of creation right here, which is an area where baby stars are being formed, just like the Orion Nebula. And you can see these little fingers here are dense gas dust pockets where the stars are currently being formed inside of them, which is pretty incredible. And you can see as we fly through here that there are baby stars hidden inside of these regions. It's hard. I don't know if the program simulates that. But you can see how this incredible structure of gas all around is forming baby stars. They're formed in these pockets. The stars eventually get so bright that they push that gas away after the gas is formed onto the stars. You're leaving an open cluster like the Pleiades. Over a long period of time, those stars are pulled away from it. There's other stars where they're in such big gas clouds, they make incredibly huge clusters. And so if we look up like a cluster here, if we can, like a globular cluster. There's globular clusters which are even bigger. I don't have time to look for one right now, but they make, they're big groups of stars, and they live their lives taking hydrogen, fusing into helium until the end of their lives, where lower mass stars like our sun become planetary nebulae, like the Ring Nebula, and higher mass stars explode, forming either a neutron star or a black hole at the center, like the Crab pulsar or the free-floating black hole we looked at earlier. And that's how stars live. That's a star's life cycle. And as I said earlier, if we start zooming, there are 100 billion such stars in our galaxy, the Milky Way here. And we're just seeing only a tiny little part of our neighborhood. And every one of the dots you see here is over the 100 billion galaxies in our universe, right? Pretty cool. So please let me know if there are any more questions. Otherwise, I'm going to finish here. I'm really happy that this was, oh, here. I think right here. Can I? Yes. This is a globular cluster. So let's go to this globular cluster. Yeah, there we go. So here's a globular cluster. This is a cluster, a much bigger cluster than an open cluster like the Pleiades. There are maybe 100,000, 10,000 stars, 100,000 stars here. And it's much older than an open cluster. These stars are much, much older. These are some of the largest structures of stars in our galaxy with the oldest stars in our galaxy. And if you were to live on one of these, your night sky would be pretty incredible. So if we were to go and click on one of them, one of these stars here, and look at its star system, it's, it doesn't actually have any planets, does it? Taurid Neptune. Yeah, let's go there. Let's go to this guy's Taurid Neptune. So this is the Neptune, and we're going to land on it and finish here. So here's the Neptune. And this is the night sky from the Taurid Neptune. We'll get out of the atmosphere so you can see what it looks like. And this is what it looks like from the surface just outside, where you can see the Milky Way, because the globular cluster is well outside of our own galaxy, and the night sky is just filled with Christmas lights of older stars of the cluster. So a supernova and a nova are very different. A nova is what happens when you have a white dwarf star that's being fed by a neighboring star, and that gas on the surface ignites because enough of it accumulates and gets hot so that the star undergoes fusion on its surface, and that burns up all of the hydrogen. A supernova is a very different thing, where you have an exploding star that is a very old star. So they're very different things. They're just both very bright for a period of time, which is why they were called a nova, and then we're like, that's different, that's a supernova. And you can see here as we crest this, in fact here we can really make it dramatic. If you want to really make a dramatic thing, we can change this. But this is auto. And as we crest, you can see this incredibly bright red star late in its life, similar to how Betelgeuse is irregularly shaped, because it's so massive, the gravity is not holding it into a sphere, perfect sphere again, as it rises, which is pretty incredible. If I look out here, we can really crank up this. Very pretty for everyone. But anyway, that's Space Engine for everyone. I hope you guys had a fun time. I had a really good time. And I will hopefully be on another one of these. I'm trying to think about making them every other week. And I'll try and cover another science topic. So this was stars. Maybe in the future we'll talk about planets, like in our solar system, or extrasolar planets. I work on galaxies and black holes, so I could talk about that at some point. But I think this is a pretty cool tool to help out. So Banana PR asks if stars get bigger or smaller as they age. And the answer is, generally, stars get bigger as they age, but only later in their lives. When a star is born, it stays that size. It might get a little pulse in and out a little bit, but when it becomes later in its life, as the core collapses because it needs to get hotter to fuse heavier elements, the rest of the star balloons outward to balance that. The core gets hotter, that heat kind of ignites, like makes the star kind of puff out bigger. And so a star will kind of puff bigger, and there's periods of time where stars get kind of have a lot of this, variable activity as they get brighter, bigger and smaller. But generally stars will get bigger as they age until they puff out into space and are left with a naked core, in which case they're much, much smaller. Or they explode. And so generally they don't get bigger like linearly like we do. It's kind of like the way that we have a rapid period of getting to our height and then we stay at that height. But unlike humans, which get a little shorter as our bones compress, stars get much larger, and so then they eventually puff out. And so when they get larger, their surfaces get cooler, but they make more light generally because they're much, much larger. But that's a good question. It's nice to see so many familiar faces in here. I'm happy to be able to do this. But anyway, let's go back to my big version of me. I appreciate you with my green screen here. Thanks to my brother for this wonderful green screen that I have here. It allows me to fly around the universe. I think this is a really fun way of doing these sorts of things. And I hope in the future that you can join me again. If you just tuned in like late, this will be immediately viewable like on my YouTube page, and you should follow me on YouTube, subscribe, or do the things, hit that like and subscribe button, I guess. I'm very bad at promoting myself. But you can click that subscribe button and you'll be notified when I go live in the future, or if I make other videos. I make other videos that are more about inspiration, and I can talk about that. But for this, I wanted you to do pure science. Just get our minds off of like the bad news of the day, and instead think about, the fate of the universe and the eventual bad news of the death of our sun. I got another one. Michael Rugarello. What happens to the speed of light as it warps around a black hole? So the speed of light is constant. It only changes when light goes through a medium like water or glass. But as it goes around a black hole, the speed of light stays the same. It just is traveling in to the light is the quickest way of, or like the shortest path between the 2 points, which around a black hole is not through the black hole. It's actually in a curved arc. But the speed of light stays the same. Time changes though. So as you get closer to the black hole, time seems to slow down. For the people watching you, for you, it doesn't feel any different. But for someone watching you, time would slow down as you got near a black hole. Good question. We'll talk about black holes. We'll go to the black hole at the center of the galaxy at one point on this. You'll have to tune in the future. If you also have other questions, you can I can add like, let's add a text thing here. I can add, you can follow me on Twitter. So at Kevin_Hainline, Twitter, and Instagram. It's just Kevin Hainline. So if I change this, make this font much, much bigger. Okay. We can put this down here. This allows you to follow me, and you should follow me because I post about these sort of things all the time. And if you have questions, just ask me. Just send me a message on Twitter, or send me a message on Instagram, which is harder for me to remember. I look at Twitter a little bit more than I look at Instagram. But you can ask me these questions, and I'll answer you. If it's a big question, I'll put an episode of this. It would be fun. All right? Thank you guys. Bye.